All right, Matthew, we're live. And everybody on the screen, thank you for joining. And we're going to wait about 5 minutes for everybody to join. In the meantime, let us know, leave a comments where you're tuning in from. Well, I'm personally based in San Jose in the Bay Area. So, Matthew, where are you tuning in from? So, Matthew, can you hear me?
Yeah. I'm sorry. Did you say where am I tuning in from?
Yeah.
I am in Connecticut. Sorry, I was just typing this in the chat.
Yeah, no problem.
I am in Connecticut. I'm an East Coast person.
Nice. So, so you have been working remotely, right?
Yeah. I've been working remotely for several years, but I'm making trips out to California pretty regularly. I'm actually going to be going out there next week, so I'm pretty excited to see everybody.
That's awesome. Well, by the way, the data engineering thing community is going to be co-hosting the engineering event stream meetup in San Jose next week on September 27th. I can post a link later if you guys want to check it out. But if we can make it, that'd be great. And I know Matthew is going to be there. A couple of friends going to be there. And let's meet and connect.
Yeah. The last time we did one of these, when was that? That was back in June in San Francisco. That was awesome. That was so much fun.
Yeah, it was a lot of people after the Data AI Summit. It was a really good one.
Yeah, I was impressed on how you all pulled that off. That was great.
Yeah, that was one also co-hosted with Mage, and they did a really good job help setting up everything, organizing everything. It was a really good time.
Yeah, Mage is actually collaborating with some Delta community members for a meetup in Japan coming up here soon.
Oh, wow.
Yeah, I'm not going to make it. I wish I was though. It's in Tokyo. Yeah.
Cool. Yeah, I noticed that a lot of companies also host meetup and events in the East Asian countries as well. So it would be really cool if we get to travel there.
Yeah. Good. It would have been a good excuse. Next time, I'll try to put in a request. Say, hey, I got to go to Japan.
Yeah, that would be really awesome. So, how has been working for Databricks so far?
It's been great. Yeah, I mean, it's kind of interesting. So, like, I've been blogging about Spark and writing open source Spark code and using Databricks for many, many years. So, it's kind of like an extension of what I was doing before, which is great. But yeah, I love working with Databricks. Like basically a lot of the people who make the PySpark and Delta Lake and all these technologies, it's great to just work with them directly. So it's been a dream come true, really.
That's really awesome. It kind of reminds me when I first joined Confluent. That was 4 years ago. And that's how I feel, because as a data engineer, like I want to learn more about streaming, and it was the company founded by the people who built Apache Kafka, and it was very exciting to be working around those engineers.
Yeah. I mean, sometimes it's like a little intimidating and humbling because you're like asking questions like, "Hey, why doesn't this work in PySpark?" And it's like the people who built PySpark, but they're also nice. It's just such a nice community.
That's really awesome. It's always good to be, in an environment professionally where it feels like it's okay to ask any question and there's no judgment.
Yeah. I mean, I'm shocked. I look at these people and I'm like, wow, you're all so smart, but they're so nice. So it's a wonderful vibe. I actually feel like the data community is kind of like that in general, though. I don't know. Has that been your experience as well?
Yep. I mean, at least I feel like when there's any discussion on LinkedIn, at least the group of people I usually interact with, I feel like everybody's pretty humble. And then, people can agree, disagree, but there's never like hard feelings or offense taking or anything. So that has been a good experience.
Yeah, that's been my experience too. I mean, sometimes I get trolled on Reddit, but I kind of like when I get
Really?
trolled. Yeah. I get trolled on Reddit, but I think it's funny. I think it's funny when I get trolled. So I'm into it.
Oh, that's really fun. And I mean, I think, I only started a post on LinkedIn like March this year. And one day I just started realizing, just like in real world, like among all the data engineers you work with, like there's nobody who knows everything. There's everybody have different strengths, and when you put together a team, people just kind of have to complement each other and learn from each other. And so it applies to the data community, like no matter it's like content creation or just in general data community where we learn from each other. Everybody have unique experience and we can all learn from each other. Like it's realistic expectation that you expect one person to know everything, and it's unfair to judge somebody just because they know something that you don't, because we all have a different journeys and done different projects in the past.
Yeah, 100% agree with that. And that's why I'm so happy you have this data engineering things. It's great. Such a positive thing for the community.
Yeah, thank you. Okay, well, let's get started. Again, hey everyone, thank you for joining. Here at Bay Area, it's a wonderful Friday morning, and we have Matthew Powers from Databricks to talk about Delta Lake. So Matthew, would you like to give an introduction to everyone?
Sure thing. Yeah, so I will actually just skip to my first slide here. So I am a staff developer advocate at Databricks. I kind of have a different path to programming than most folks. I actually worked in finance for 5 years before I started programming, and then I kind of just taught myself how to code. Started out as a Ruby on Rails web developer, and then just ended up switching into data engineering when the startup I was working for started kind of drowning in data. I'm a longtime Spark blogger, so you might have seen me on the interwebs before. Also have created a bunch of popular open source Spark libraries and written a couple Spark books, and here I am. So happy to be here.
Awesome. Yeah, well, thank you for joining us, Matthew. I would say for the next step, please feel free to go ahead with your presentation for the Delta Lake.
Perfect. Yeah, so let's talk. I'm going to give a little overview about myself. Then we're going to go through the agenda, and then I'll talk for about 40 minutes. So I'm pretty excited to chat about everybody. So here are some of the open source Spark projects that I've created by myself and with the community. The ones I will call out are Quinn and Chispa. So Quinn is a bunch of PySpark test helper methods. Oh, no, sorry, that's Chispa. Chispa is the PySpark test helper methods. Quinn is a bunch of just kind of PySpark, mainly data frame helper methods that are pretty popular in the community. If you're into open source code, ever want to contribute with Spark or Delta Lake or any of these kind of smaller open source libraries, let me know. I love collaborating with new people. Okay, so here's what we're going to talk about today. We're going to chat about an overview of Lakehouse storage systems, kind of what Lakehouse storage systems are and why they've become important in this modern data engineering landscape. Then we're going to talk a bit about Delta Lake and PySpark, which is just one of the engines that can communicate with Delta Lake. And then we're going to chat about Delta Lake and other computation engines, such as Trino, Flink, Pandas, Polars, and Dask, and talk about why Delta Lake offers some really nice features for other compute engines as well. So we're kind of getting started, just motivating this Lakehouse storage system conversation with like why Lakehouse storage systems exist. So we have different types of file formats. So we have JSON, CSV, Avro, which are row-oriented file formats, Parquet and ORC, which are column-oriented file formats. And column-oriented file formats are really nice because let's say you have a data table with like 200 columns, and you just want to query 2 of those columns. When you use a column-oriented file format, you can easily cherry pick the data in those 2 columns. So that's why you'll see a lot of times for a Lakehouse storage system, their preferred file format is a column-oriented file format like Parquet. So this slide kind of talks about the big Lakehouse storage systems and the difference between the data lake file formats. So we have Delta Lake, Iceberg, and Hootie, which are the popular Lakehouse storage systems. And those are kind of different but a related concept to file formats like Parquet, ORC, and Avro. So basically, a Lakehouse storage system consists of a metadata layer plus data that's stored in a file format. And I think most of these Lakehouse storage systems store their data in Parquet. Okay, so now let's take a quick look at the evolution of data storage methodologies over time, kind of how data used to be stored and why we've kind of evolved to different types of architectures over time. So if you look on the left there, the first generation platforms were data warehouses. So organizations were kind of ETLing into a data warehouse, and in that data warehouse, they were running their BI and reporting workloads. Now that worked great when organizations were not doing advanced analytics and the data set sizes weren't huge. So let's say maybe around 2015-ish, a lot of organizations started getting a lot more data. They started wanting to do advanced analytics. I mean, it depends on the organization, of course. Many were doing this far earlier. Some are still catching up. But then organizations started switching to kind of this two-tier architecture, which is that B, current two-tier architecture. And then they started having data lakes. And the reason they were using data lakes is so that they could start doing advanced analytics workflows, data science and machine learning on the data lake. But in parallel, they were also still had their data warehousing architecture. So they were ETLing from the data lake into the data warehouse, and they were using that data warehouse for BI and reporting. Now, as you can imagine, this two-tier architecture was highly problematic from a cost perspective, right? Because you're storing the data in the data lake and the data warehouse, but also from a violation of the data management single source of truth principle, right? When data is stored, the same data is stored in two different places, it's inevitably going to become unsynced. When it becomes unsynced, then you're going to get different query results when you query the data lake and the data warehouse, and the standard violation of the single source of truth data principle. Whenever you do that, you're going to get some pain and suffering. So now what organizations are doing is they're migrating towards Lakehouse platforms. And what this does is organizations are storing data in a Lakehouse storage system, such as Delta Lake. A Lakehouse storage system is kind of a metadata layer and the data itself. And directly on the Lakehouse storage systems, you can run your BI, reporting, data science, and machine learning. So you're not duplicating your data. This is operationally easy. It provides nice interfaces like the SQL people who want to be doing BI and reporting and just live in SQL world. They can do that. You have nice integrations to the BI tools. You have low latency queries, and you have the flexibility to perform advanced analytics. So if you'd like to read more about the architectural paradigms around this and how the world has migrated towards this Lakehouse architecture, I highly recommend reading this paper. It's around 10 pages, and it's definitely worth reading. Okay, so let's look at more about data lakes and why they're problematic. So if you have a bunch of parquet files sitting in storage, why is that a very painful workflow compared to a Lakehouse storage system? So in order to query a bunch of parquet files sitting in storage, you need to first list the files. Now, if this data is stored in a Unix-like file system, maybe that file listing operation isn't too slow. But if this data is stored in a key value cloud object store like AWS S3, that file listing can actually be really slow. So I used to work on a data lake that had 20,000, 30,000 files, and that file listing operation was of the order of like 4 minutes. But if there's nested directories, key value object stores are actually really bad at globbing, and file listing operations can take tens of minutes, even hours. So file listing operations are slow. Even simple operations like deleting a couple of rows from a data lake are hard. It's hard to perform the operation in an efficient manner without overwriting the whole lake. So the code is kind of uncomfortable, and that kind of extends to all DML operations are tough on a data lake. Data lakes don't have ACID transactions. We've all had our Spark clusters blow up mid-transaction. And when you're writing to a data lake or performing any sort of data mutations to a data lake, and your cluster blows up mid-write, then you have these partially written files, and your overall lake is corrupted, which is very uncomfortable to clean up. So you definitely want ACID transactions to avoid data corruption. So these are kind of just 4 flaws with the data lake. Basically, they're painful to work with. And in this day and age, because there's so many great Lakehouse storage systems, you'd never really want to work with a data lake. Let's take a look at the contents of a Delta table, how it's architected at a high level. So a Delta table consists of data that's stored in parquet files. So in that sense, it's similar to a data lake. But in addition, it has this metadata transaction log, which allows for DML operations. It allows for ACID transactions. It allows for a bunch of convenient helper functions, some of which we're going to cover in this talk. So what is Delta Lake? Delta Lake is a protocol. This protocol is currently implemented. Well, it has 2 official implementations, many unofficial implementations. One of the implementations is in Scala, and that implementation is used to provide the Scala Spark, Java, and PySpark interfaces. We can look at the download stats and see that this open source library has been downloaded 112 million times. So it's quite popular. The proof is in the pudding. Obviously, it's getting lots of open source downloads and being used in a lot of open source contexts. In addition to this Delta implementation that's in Scala, there's also the Rust implementation. Now, the Rust implementation has been downloaded 19 million times. And that one's really cool because it provides bindings for libraries like Pandas and Polars. And those bindings do not depend on Spark, which also means they do not depend on Java. And it just goes to show that Delta, I think sometimes folks think Delta is highly intertwined with Spark, and it is, but not necessarily. You can use Delta without Java, without Scala, and without Spark, and a lot of people are doing it apparently because that implementation has 19 million downloads. Okay, I'm just gonna check my time here really quick, make sure I don't blab on too long. So we can see that Delta Lake can be installed in 2 different ways for Python users, depending on the execution context. So if you're going to use Delta in a PySpark context, the correct command is pip install Delta Spark. But if you want to install Delta without Spark, then you just do pip install Delta Lake. And the key takeaway is you do not need Spark to enjoy the benefits of Delta Lake. At the end of this talk, we're going to show how to query a Delta table with DuckDB and Pandas and Dask and other engines. And you'll clearly see that Delta tables can be queried by multiple engines. Okay, so now we're moving to the part of the talk where we're going to look at how to query Delta tables with PySpark. Now, a lot of these interfaces, the syntax is a little different if you're using this sort of functionality for Pandas, but it's the same idea. But just for purposes of this demo, we're using PySpark. Okay, so let's look on the left side of this slide, and we suppose we have a Delta table with 3 different versions. So version 0 of the Delta table is just a single column data set with 3 rows of data, 0, 1, and 2. And then version 1 of this Delta table is going to have 3 additional rows of data, 8, 9, and 10. We go from version 0 to version 1 by performing an append operation with those 3 additional rows of data. And then we look at version 2 of this Delta table, and that contains 3 rows, 55, 66, and 77. So version 2 of the Delta table has been constructed with an overwrite transaction. So basically that's going to say, hey, we're going to remove all the existing data, add this new data. So if you turn your attention to the top right of this slide, we can see when we read in this Delta table with Spark read format Delta load, we can see that by default, we're going to read the latest version of the Delta table. Now, if we look in the bottom right of this slide, we can see that we can easily time travel back to version 1 of this Delta table. So what we do is we just perform the same read operation, but we set the option version as of 1 parameter, and that's going to return the data set with 0, 1, 2, 8, 9, 10. The order is not the same in the read, but that makes sense because Spark guarantees no particular order when it's reading files. So this is really cool. One thing to dig into here, and is a good way to kind of think about the difference between a data lake and a delta table. So when we created version 2, right, we didn't delete the files from version 1. We can see that because we're still able to time travel back to version 1, and we can see that those files still exist. So now it's good to get yourself in this thought process between differentiating between logical operations and physical operations. So when you're dealing with a data lake, you're going to physically delete version 1. You're going to write the data files in version 2, and you're not going to have this ability to time travel. But when you're dealing with a Lakehouse storage system, you're not going to physically delete the files from version 1. You're going to logically delete them in the metadata layer, which is basically just saying marking those files for deleted, but you're not going to physically remove them from storage. It's very important to understand the difference there when you're working with Lakehouse storage systems. We're not going to be able to get into that in too much detail, but just know that when you're dealing with Lakehouse storage systems, there's a difference between logical and physical operations. When you're in the data lake world, you're kind of just dealing with physical operations. Okay. Let's look at schema enforcement and how Delta Lake enforces schema by default. So let's suppose we have a Delta table with 3 columns, C1, C2, and C3. And let's suppose we have a Spark data frame with 3 different columns, C1, C2, and C5. So I guess 2 of those columns overlap, 1 is different. So now let's suppose we try to append this Spark data frame to this Delta table. Now what's going to happen is we're going to get an analysis exception, and basically this transaction is going to be rejected. And what Delta Lake is going to be saying is, hey, you can't append this data frame to this Delta table. The schema is different. You haven't told me that this is acceptable, so I'm blowing up and not going to let this happen. Now, this is actually really great and useful. Again, when you're comparing this to a data lake, right? Data lakes are easily corruptible because there's no schema enforcement checks unless you add them manually. But out of the box, there's no schema enforcement checks. So you can append any data you want and easily corrupt your data. Okay, but let's suppose you do want to kind of append some data with a different schema. That actually is possible, and that's called Schema Evolution. So if you look in the top left of this slide, let's suppose we have a Delta table with 2 columns, first name and age. And then in the bottom left of the slide, we have some data to append. So we have first name, age, and country. So basically, the data we would like to append has this additional country column that our existing Delta table does not have. So if we look in the top right, we can see that if we try to append this data frame that has a mismatched schema, we're going to get that exception and data won't be appended. And that's schema enforcement. And we've discussed in the previous slide how oftentimes that's desirable. But in the bottom right, we can see that if we want to enable this schema evolution, enable this data frame with a slightly different schema to be appended, all we need to do is set this option merge schema true parameter, and that's going to let this schema to be this data frame with slightly different schema to be appended, and it's going to give us this really nice result here. Now, in a data lake, you technically can, using Spark, you technically can append data with different schema, but every time you read it, you need to specify a parameter to make sure it gets read properly, which is definitely not what you want. I'd almost consider it to be an anti-pattern. So anyways, Schema Evolution and Delta's implementation of it is great, very useful. Back in the day, a lot of people would rewrite entire data lakes when they wanted to add a column, which was obviously highly inefficient. So Schema Evolution is a very handy feature. Okay, let's look at another feature that if you're a database user, this just seems trivially easy. But for data lake users, this is not easy at all. So suppose you have a data set with 2 columns, first name and age. And then suppose you'd like to delete all the rows with age greater than 75. So with Delta Lake, you can just run this delete command and say, hey, whenever the age is greater than 75, delete the rows. Now, under the hood, Delta Lake is going to perform this operation very efficiently. One other thing that's very nice about Delta's handling about DML operations like this is that while the DML operations are taking place, you can still read the data, and that's no problem. Now, for data lakes, while a DML operation is taking place, if you try to read the data, that you can get incorrect results or corrupted results because you can't read the prior version of the data while the DML operation is taking place. Let's take a look now at Delta Lake constraints, which kind of make your Delta table always be in a clean, pristine state. So let's suppose you have a Delta table with an age column, and you'd like to make sure that there's no negative ages that are added to that age column. So in this case, we can just run a SQL command to add a constraint. We're naming this age is positive. And the check we're applying is that the age is greater than or equal to 0. So if we have this constraint on a Delta table and we try to append a data frame that contains a first name and age columns, and one of the rows has an age that's negative, basically what Delta is going to do is blow up and say, no, you cannot append this data. We're not letting you corrupt your table and append data that makes no sense. Constraints are very handy. You see on LinkedIn a lot, people are talking about data contracts. I think constraints are one of the best ways to kind of make a pseudo data contract or part of a data contract, as well as schema enforcement, because you can't, like, they talk about these data contracts and specifying a lot of these rules in YAML files. You know, you get a lot of these data contract features out of the box with Delta, which is really nice. Okay, now let's talk about bin packing small files in data lakes and how to do this. So let's suppose we have a situation where we have a Delta table and there's like eight parquet files. The data is stored in 8 parquet files. 5 of those parquet files are super tiny. These ones over here. 2 of these parquet files are kind of medium sized, but still too small. And 1 of these parquet files is perfectly right-sized. Now, if you have an excessive number of small files in a big data system, that's going to create an unnecessary I/O overhead when you're reading the data, and the query is going to be slower than it should be. So what you're going to want to do is get this data set into 3 right-sized files. So this is called bin packing or small file compaction. And there's a variety of reasons why small files are created. Streaming systems, frequent updates, and hive-style partitioning are the main culprits typically. So anyways, we can run this simple Delta command, which is just optimize execute compaction. And what that's going to do is take the excessively small files and repackage the data into larger files. Oop, I'm going to plug in my computer. Hold on one second. So this is called bin packing. Very easy with Delta. Again, a nightmare with data lakes. So at this point, you are probably convinced that Delta Lake is awesome. And if you have a Parquet data lake, it's very easy to convert it to a Delta Lake. So all you need to do is run this convert to Delta command, and it's going to convert a Parquet lake to a Delta Lake. Now, something that's cool about this, and since we've learned about the architecture of a Delta Lake table, we can kind of know about how this transaction is executed. Like, right, so all a Delta table is a metadata layer and a bunch of data stored in Parquet files. So in order to convert a Parquet table to a Delta table, you don't need to rewrite the data. The data can stay where it's located. It doesn't need to be moved or rewritten. All we need to do is add that transaction log metadata entry that has the metadata about the files, and then all of a sudden it's a Delta table. Okay, this is kind of a more trivial example, and unfortunately I will not have the bandwidth or time to go through all of the Delta Lake commands. I'm just going to show this one because it goes to show how Delta offers, you know, transactions and functionality that data warehousing SQL engineers would come to expect. One is this create table like. So if we have a delta table with 4 columns, and if we want to create another delta table with the same exact schema, we can just run this create table like, and then that'll make a delta table with the same exact schema that's empty. So it's not a particularly impressive command, but I think it's just representative of the breadth of SQL commands that data warehousing engineers expect to exist, that do exist in Delta. Okay, cool. So I'm actually going to have to skip over some of these slides to skip to what I want to talk about with the Mac library. These are basically merge commands, complicated merge commands. This is talking about the Delta Lake change data feed. I wish I could talk about all those slides, but I can't for time constraints. Okay, so now we are shifting over to Mac. So Mac is a library I am developing with the Delta Lake community. It's an open source library for PySpark and Delta. And basically what it does is provide some quality of life Delta helper methods that are really cool and make the life of Delta users easier. And if you're interested in collaborating on this, we are definitely taking pull requests. So let's take a look at some of the functionality that's offered by Mac. So let's suppose we have a Delta table with col1, col2, and col3. And then let's suppose we have some data to append in the data frame, also with col1, col2, and col3. And we can see that the data that we would like to append, the first row of that data, has a duplicate col1 value. So for whatever reason, when we're appending to this table, we don't want to append to duplicate col1 values. We want to enable for col1 to be unique. So in this case, we can use this Mac functionality to append with no duplicates. So this is the Mac append without duplicates function. The arguments that we supply are the delta table, the data frame that's being appended, and the columns where the uniqueness is important. And what we can see is after we run this operation that the data has been appended, except of the 3 rows that were meant to be appended, only 2 of them were appended. So we did not append duplicate data. Now, this is a great way to make sure you do not append duplicate data to your table. Mac makes this easy. You can do this. Of course, this functionality uses merge under the hood. So you can also just write the merge logic yourself. But I think that it's a little bit cleaner to invoke the append without duplicates function. OK, let's look at how to drop some duplicate Delta Lake rows with Mac. Deduplication, such a common data engineering operation. So let's suppose we have this Delta table with col1, col2, col3, and col4. And in this case, our primary key is col1. And the columns that we're interested in not having duplicate values are col2 and col3. So col4 is not being included when we're thinking about this duplicate value. So we can see that there's a lot of rows in this data set with col2 and col3 being duplicated. We can see AA in multiple of these rows. So in order to perform this operation, we just run this Mac drop duplicates function. We specify 3 arguments. The first argument is the delta table object. The second is the primary key column. And the third is an array of the columns that we're checking for deduplication. And we can just see that Mac is going to perform this deduplication logic for us, no problem. Again, you can do this with the merge statement. It's going to be a lot of kind of messy code. Mac drop duplicates kind of makes this easy. Mac also makes it easy to perform type 2 SCD upserts. Now you might think, hey, type 2 SCD upserts, who cares about that now that we have time travel? It turns out that type 2 SCD upserts, even in the modern world, are useful because of vacuum constraints and other things that are outside the scope of this talk. I'm not going to be able to talk about the theory behind type 2 SCD upserts too much, but we can see that in that step 3 right there, we can just invoke this type 2 std upsert. We supply the path to the table, the update table, the primary key column, and the attribute columns. And that's just an easy way to perform a type 2 std upsert on a Delta table with a single line of code. Okay, cool. So I need to move on to the next thing. I will quickly talk about this slide, which is appending to a Delta table with constraints. So let's suppose we have a Delta table with some constraints. So this little Delta table has 3 columns, col 1, col 2, and col 3. So the constraints that have been applied to this Delta table are that col 1 has to be greater than 0, and col 2 has to not be equal to z, the string z. So now let's suppose we want to append some data to this table. Some of this data is passing the constraints, others are not. Now, we saw before how Delta tables allows for constraints to be applied, and you try to append, and basically if any of the rows violate that constraint, the entire transaction is rejected and nothing gets appended. Now, I was talking with the Delta Lake community, and we were kind of chatting about how, well, a lot of times you don't want to completely reject the transaction. You want to apply all the rows that satisfy the constraint, and maybe the rows that don't satisfy the constraint, you want to throw those in a quarantine table for further processing or analysis. So Mac has this constraint append method. So you apply it, you supply it with 3 arguments. One is the Delta table. One is the data where we would like to append the data frame with the data to append. And then the third argument is this quarantine table, which is where we want to put the data that doesn't satisfy the constraints. So basically, when we run this append operation, all of the data, in this case, the 4 rows that do satisfy the constraints are appended to the data. And then the 2 rows that don't satisfy the constraints are appended to a quarantine table where we can do further analysis, debugging, or pre-processing. I guess ideally what we're going to want to do is clean the data and then append it later if that's possible. Okay, so let's move on to using Delta Lake without Spark. So all of these slides that we're going to talk about from here on out are going to be using the Delta Rust library, the Python bindings of the Delta Rust library. And this does not depend on Java, it does not depend on Spark. Okay, so let's look at how to run a Pandas query significantly faster using Delta Lake compared to a CSV file. So let's suppose we have a 5 gig CSV dataset, and this is going to consist of 9 columns. This dataset, you might have seen it before. This is part of the H2O benchmarks. This is the group by dataset. Very handy dataset to have in your local machine, by the way, for benchmarking purposes. So this 5 gig dataset has 100 million rows. And as we can see in step 2, we want to run a Pandas query. So we're going to use the Pandas read CSV function, read that CSV file into a Pandas data frame using use calls to make it run a little bit faster. Basically what use calls does is make sure it doesn't persist unnecessary data in memory, right? So like for this query, we're only using ID1, ID2, and V1. So those are the only columns we need to persist in memory. So we're going to run this filtering query. So we only want rows where ID1 is equal to this value, ID016. And then we're going to group by ID2 and then run this sum aggregation. So when we run this query on a CSV file with Pandas, that takes 20.6 seconds, so pretty slow. And now let's see this same query on a Delta table and using Pandas, the Pandas query engine, and see how much faster it can run. So in this case, we are instantiating a Delta table object, and this is on a Delta table that's been z-ordered. We'll talk about that in a second. I'm just going to go through all the lines of code here because this is kind of interesting to see how this Delta RS library is providing this interoperability with all these query engines. So when we have this Delta table object, we can invoke this toPyIO dataset method, which is going to kind of export this dataset as a PyIO dataset. Then we are going to supply a condition, which is kind of this PyIO compliant way of specifying a condition. So then what we do is we take this data set and we convert it to a Pandas data frame and then run the same query as before. And we can see that this only takes 1 second to execute. Now, let's kind of examine why this is the case. So Delta tables consist of data that's stored in Parquet files and a metadata log. So what we've done is this data was previously stored in a single CSV file. Now we've broken up this data set into multiple Parquet files. And then what we've done is we've z-ordered the data, which basically co-locates similar data in similar files. Now, since we've co-located similar, and we've z-ordered on the ID1 column, which is what's being filtered on. So now we've co-located the similar data in similar files. So the ID 016, ID1 equals ID 016 rows of data have been co-located in the same files. So now when we execute this transaction, we only need to read in a fraction of the data. Now, we know we can read in a fraction of the data by consulting the Delta Lake metadata layer. And if the min and max values of ID1 are such that we know it does not contain any values, where ID1 is equal to ID 016, we can skip that file entirely when we're executing this query. That's why we get this wonderful speed up. Cool. I'm only talking for 4 more minutes, so let's make this quick. I'm actually going to skip over this Dask one. Same example. Dask can be run quicker with this. Let's take a look at polars. So here we have polars. This is the same data set as before, but instead of running it on the 100 million row data set, which was 5 gigs, we're going to run this query on the 1 billion row data set, which is 50 gigs. All these computations are run locally on my local machine, by the way, which has a MacBook M1 with 64 gigs of RAM. So we have this same data set as before. And here we are going to query this CSV file and measure the runtime. And we're running the same exact query as before. We're looking at all of the rows where ID1 is equal to ID 016. Then we're going to group by this ID1 value. We're going to run a sum aggregation on the V1 column, and then we're going to collect the results. We can see that polars can execute this query in 30.4 seconds, which is very snappy, considering this was 10x the size of the data set that the Pandas query is run on. Now we can run this same query on a Delta table. Here we're using scan Delta. Scan Delta, there's 2 when you're using polars, by the way. There's read Delta and scan Delta. Scan Delta allows for more queries to get pushed down, so that's generally what you're going to want to be using. We're running the same filtering operation, and then we're doing the group by, aggregation, collect the results, and we can see that that's going to be running 30 times faster. Now, the reason the polars query runs faster on a Delta table compared to the CSV file is the same reason the Pandas query is running faster, because of data skipping. One thing to note here, I meant to note this before. So in this case, ID1 has, the ID1 column has 100 distinct values. They're evenly distributed. So when we're doing call ID1 is equal to ID 016, we are only looking for 1% of the data. That means in theory, we can skip 99% of the rows in the data set to run this query and still get the accurate result. So this is a bit of a contrived example. And one thing to note, but it's still useful, because a lot of times you can skip huge amounts of your data set when you're running queries based on filtering predicates. Now, one thing to note here is that if you're unable to skip data skipping is obviously not going to help make the query faster, right? So Delta Lake enables file skipping based on metadata information. I'm using examples that highlight that feature. But obviously, if you can't skip any data, you shouldn't expect to see those huge performance gains. Okay, we're wrapping up here. Let's just see quickly how to query a Delta table with DuckDB. So we can instantiate this Delta table object. Again, that Delta table object is from the version of Delta that does not depend on Spark. It's the Rust implementation. And then how do we get this automatic interop with DuckDB out of the box without even building an official connector? Well, Delta tables can be converted to PyRO datasets. DuckDB is capable of reading PyRO datasets. This is wonderful interop out of the box for free. I think DuckDB is a great example of a query engine that's very well architected and also has some great out-of-the-box features like the ability to read PyRO datasets. And it's awesome that we can just query Delta tables with DuckDB, no problem. Okay. This is the last slide we're going to cover before we wrap this up. And this kind of covers what I'm trying to hit with this talk is the Lakehouse architecture and how multi-engine query support is critical for building the Lakehouse architecture. So in this first step here, we're creating a Delta table with PySpark. This has 2 rows, Bob and Sue. So we append that data to a Delta table. Of course, the Delta table with PySpark depends on Spark and Java. Now, in step number 2, we are appending to this Delta table with Pandas. So we're just appending a single row of data to this Delta table with Pandas. That's great, no problem. Of course, we don't need Spark to perform that operation. And then we're finally reading this Delta table with polars, and we can see we're getting the 3 rows of data as expected. Now, what's so cool about this is we can see we're operating on the same table with 3 different query engines. No problem. Some depend on Spark, others don't depend on Spark. And I think that this is the real essence of the Lakehouse architecture and what a Lakehouse storage system like Delta Lake enables, because you can operate on tables using multiple query engines, no problem. Cool. So feel free to follow us on LinkedIn if you'd like to learn more. This is kind of an old image. We have tons of more followers now. You can follow me. I've been pretty inactive on LinkedIn, but I'm going to try to get back in there. Check out blog posts on Delta Lake. And if you'd like to learn more about the different Lakehouse storage systems and kind of a comparison of them, feel free to read this post, which has some cool benchmarks. Cool. Looking forward to questions.
Yeah, thank you so much, Matthew. I personally big fan of all the coding examples you gave in your presentation. I think that's super helpful. You just can see exactly, what kind of operations or code you might run, and then how that works out with Delta Lake. So that's really awesome. And actually, a couple of folks has asked for slides. So maybe you can share with the LinkedIn event, right? Once we're done with the session.
Yes, of course.
All right, cool. So let's look at the question. Okay, so first question, that's come from a YouTube viewer. So do you have resources that someone who's new to Delta Lake but have experienced Spark can use to run Delta Lake on local PC mode?
Yeah, great question. We are trying to get a new getting started guide in the website. So if you go to the Delta Lake website, there's a getting started guide. It's not the easiest. So like, unfortunately with Spark and Delta Lake, you need to install a lot of stuff locally. And it depends on which software you're using, what the instructions, right? So if you're using SBT and Scala, there's different, if you're trying to use, Conda and PySpark and all that stuff. But I think that if you're using PySpark, the best place to get started is going to be the Delta examples repo. So let me actually pop this in the chat, Delta examples. It's a little uncomfortable provisioning a machine to run Spark in general. I don't know. Is that chat example suitable?
Oh, let me post on LinkedIn.
Yeah, it's best if I get on LinkedIn. too. Let me.
Okay, I already posted. No worries.
Sweet, thank you.
Yeah, no problem.
But yeah, those basically, if you can get your local machine provisioned and run those Jupyter notebooks, that's the best way to learn Delta Lake, in my opinion. I'm one of those people, I can't like really learn something until I run the code myself locally. That's how my brain works.
Yeah, I know what you mean.
Yeah.
Well, I mean, sometimes you can read a book and read through all the examples. It feels like, oh, I know how to use Spark now, but you don't really until you actually run some code.
Yeah.
Practice with some real-time data, run into problem. Cool. One more question. So, well, first of all, thank you so much, Matthew, for your time. Are there any cases you would recommend using Pandas instead of PySpark when building transformation in Databricks? Or maybe this is talking about Delta Lake specifically as well.
Yeah, I think. Well, I'm a huge fanboy of Polars. I think it's an awesome library. I think it's cool. Like, obviously, Polars is not going to scale out to large data sets like Spark does. I'm like, yeah, for me, perhaps my feelings are biased, but for me, I like Spark because it's fast on small data sets and it's scalable to large data sets. And from my experience, I never know when a data set is going to get huge. So like for me, if I'm building a production system, I'm never like, oh, I know for sure this data set's going to be small enough for Polars forever. So then I'm always like, I would rather just build it with Spark. So if my data set gets larger than I expected, it can scale. So for me personally, I love Polars. I think it's great. But in production use cases, I always default to Spark because I just like stuff that's scalable because I just view the future as so unpredictable. But I think Polars is great. I love it.
All right, next question. How does a lakehouse like Delta Lake support both ACID and easy, flexible, and cheap storage for different structure type of data?
Great question. So how does it support ACID transactions? So in order to support ACID transactions, you need a reliable transaction locking mechanism. The reliable transaction locking mechanism actually depends on each of the different clouds, like how Delta Lake implements that. So it's kind of interesting, like for AWS S3, there's not like a put if absent function actually. So that needs to have a different implementation than Azure. So how does Delta Lake support ACID transactions? Basically, the short answer there is it depends on the cloud. Now, how does Delta Lake have cheap storage? So like you can store data in a data warehouse. They're going to charge you a lot per gig, right? A Delta table is stored in S3. S3 charges you a comparatively tiny amount per gig. So that's why Delta tables are so much cheaper than storing that data in like a managed warehouse or a managed service provider. Yes, I think that's the answer.
Cool. I noticed that your shirt even talk about Spark on ACID.
Yeah. I love this shirt. I like it's funny because like all my clothes are like Delta Lake clothing now, and my friends are like, "Can you stop wearing Delta shirts?" And I'm like, "Sorry, that's all I have now."
It's funny. So Dustin asked this question: are there any plans to develop Mac bandings for other languages?
Yes, great question. I actually have a sister project. So I've done this with multiple projects. Whoops, send you this link. This project is driven by two amazing developers. So Jody is the Scala bindings for Mac. One thing I've done, this is kind of like getting nerdy, super technical, but it's still kind of fun to talk about. So, right, like how Spark is developed, right? Spark is written in Scala, and then they use Py4j to expose Python bindings. So like I had created a couple of popular Scala libraries, Spark Fast Test and Spark Daria, and I could have just exposed use Py4j to expose those bindings, but I thought it was better to like write them natively in PySpark, just because I thought it's like better for the Python audience. Python people don't like looking at Scala code that's been exposed with Py4j bindings. So I could have done that, written the Jody code and then exposed it with the Py4j bindings for Mac, but we intentionally decided to not do that. But anyways, I'm talking way too much, nerding out on this way too much. Jody is the project with the Scala bindings. Would love to have you to contribute there. We got a really cool community of Scala devs working on that. Just a related point, actually, and I think that this is related to the future of data engineering in general. So like we were talking about Delta RS, and Delta RS is implemented in Rust, but a lot of most Python users are using it. They have no idea that it's implemented in Rust, because they're just doing pip install Delta Lake, and they're just using it with the Python bindings. Now, there's a really cool library called like Py03, which is how you expose Python bindings to Rust libraries. And it's so nice and fluid how that works. And I kind of view that as like the future of a lot of these data engineering libraries, like Polars is the same way, where it's written in Rust. But I think most users are using the Python bindings with this cool like Py03 library, which is exposing the Python interface that way. I kind of view that as the future of the data engineering world. Rust libraries with Python bindings.
Cool. One more question I think that's interesting. How well does Delta Lake work with kind of ingesting very nested and repeated JSON records?
Nested and repeated JSON records. Yeah, that's a great question. So like, right, a Delta table can store nested data, right? I'm personally a flat data kind of a person. I like flattening data before persisting it in the Delta table. So it kind of depends how you take it there. For me, I'm a big like let flatten before you persist. I think that when you look at like how Delta table stores like column metadata statistics and file skipping, I just think the less nested data you persist, the less headache you have, although that's not possible at all times. Sometimes you need to persist it. And then with regards to repeated JSON records, a lot of times you don't want to store repeated data. And what you want to do is, rather than doing the simple append, you want to do the merge append, similar to the Mac approach, like append without duplicates. To me, that's the best way to do it. I mean, I'm assuming that's what you're getting at with the repeated JSON records, right? Like with Delta tables, if you just append data, you can just append duplicate data, no problem. But I think it's better normally to deduplicate when you're appending. So I don't know I hope that answers the question.
Yeah, one perspective I want to add is, and I'm not sure this is, I don't have a lot of experience with Delta Lake specifically, but if your underlying data is Parquet, I know the Parquet format itself is super optimized for extracting a subset of field from a nested field. So if you're using a Parquet format underneath it, so in a way, you're getting the benefits of Parquet's optimized performance with nested field. But also at the same time, I think it depends on like kind of which layer, what's your user facing. Honestly, I think most of the core table that you want to produce for most downstream consumers, I think a flatter is a lot better format. It from a data discovery or processing perspective, but also at the same time, a lot of data, for example, like a transactional type of data you get from your upstream engineering team, because their format is very nested JSON. So as part of the transition process, maybe when you have the relative raw data, you might want to add like a nested kind of schema for your table before you do some transformation and make that flatten. So I felt like sometimes it's unavoidable, but I usually try to make my data that like the final output core table to be more flattened.
Okay, so we have a similar approach then. But you can persist the nested stuff. Yeah, and sometimes reality is nested. Like I saw this Data AI Summit talk by an engineer once, and I think this was for some Apple data, and it was like nested 40 levels deep. And I think that's reality, and they have to store it like that. Like they can't get past reality. And I think that a lot of the optimizations actually that came to Spark were due to that use case.
Yeah. All right, we're right on time. So Matthew, I see that there's actually a couple more questions on the LinkedIn even, and also on YouTube. If you have time after the session, feel free to take a look at the comments, and maybe you can reply to them offline. But well, thank you everyone for joining. We're right on time, and thank you, Matthew, so much for this presentation. And hopefully, maybe we'll bring you to our webinar again in the future, talk about something even more interesting.
PySpark. I'll come back and talk about PySpark.
All right, okay. Well, thank you, Matthew. Thank you, everyone.
Thank you, everybody. Bye.
Bye.